In this video, we're going to talk about some geometric properties of the cross product. And these geometric properties are going to explain why this is a useful vector for us to work with. Before we do that, I want to just reiterate that the cross product is only defined in 3 space. Now, I've said that, I've emphasized that. I want to just take a quick look at why. Let's suppose that we are in 2 space. Let's say I have 2 vectors. Let's let v be 1, -3, w be 2, 4. If I tried to generalize the notion of the cross product of these 2 vectors in 2 space, I would form a matrix where the first row of my matrix would be my special unit vectors. In this case, it would just be I and j because we're in 2 space, so there's no k. So that would be the first row of my matrix, and then I could put v in the second row and w in the third. And I hope right there you see what the problem is. That's not a square matrix. If it's not a square matrix, the determinant is not defined. This has 3 rows, 2 columns. If I wanted to get a square matrix, I'd only be allowed to use one of my vectors in 2 space because the other row is taken up by those unit vectors. So I can't form a square matrix, I can't take the determinant of the matrix that I can form, and therefore the cross product doesn't make any sense. Okay, so now let's talk about the geometric properties that we have when we are in 3 space so that the cross product does make sense. Now, a vector is determined by its magnitude and direction. So we're basically going to have 2 useful properties, one of which is going to tell us the significance of the direction, although I'm going to state that property algebraically so that it also covers the case that we have the 0 vector, which does not have a unit vector associated with it. And then we'll have another property that will tell us the significance of the magnitude. Theorem 8 is the one that basically gives us the significance of the direction. And it says this: if A and B are vectors in 3 space, A cross B, their cross product, is orthogonal to both A and B. Now, remember the definition of orthogonal is an algebraic one. So this says that A crossed with B dotted with A is going to equal 0, the number. Now, we can write that by saying A cross B is orthogonal to A. This symbol you've probably seen before to mean perpendicular. When we use it with vectors, it doesn't mean that. It means is orthogonal to. Orthogonal to. Okay. Now, if these vectors are both non-zero, that will mean that they're perpendicular. But this symbol does include the possibility that one or both of the vectors is 0, so it really just means that the dot product is 0. And of course, then we've also got that A crossed with B. If I dotted it with B, that would also give me 0. So it's mutually orthogonal to both of those vectors. All right, now we'll see in a little bit that this cross product will itself only be the 0 vector if either A or B is 0, or if they're parallel to each other. So if A and B are both non-zero and not parallel to each other, then the cross product will be orthogonal to A and B in the sense that it's actually perpendicular. So it allows me always to find a vector that's mutually orthogonal to the 2 vectors that I'm crossing. In the case that those 2 vectors are non-zero and not parallel to each other, it allows me to find a vector that's mutually perpendicular to those 2 vectors. That's pretty neat. Now, that doesn't tell me completely what the direction is. Let me just illustrate that. Okay. If I have this vector here, we'll call this black marker A and this blue marker B. If I wanted to take their cross product, they're not 0, they're not parallel to each other, but there are 2 possible directions that I could get, because this direction would be mutually perpendicular to those 2, and so would this. So knowing that the cross product is mutually orthogonal to the two vectors I'm crossing narrows the direction down to one of two possible directions. There's actually a rule for determining which direction it is, and that's called the right-hand rule. So here's how that works. If I'm taking the black marker and crossing it with the blue marker, in that order, black crossed with blue. If I take my right hand, I'm going to point the fingers of my right hand in the direction of the first factor in my cross product. I'm going to curl those fingers towards the second factor. So I'm curling them towards the blue vector. My thumb will point in the direction of the cross product. So if I did black marker crossed with blue marker, the cross product would point in this direction, upward. Now, if I did it the other way, if I wanted to do the blue marker crossed with the black marker, again, I take my right hand. Now, if I try to point my fingers in the direction of the blue marker, if I do it this way, my fingers don't curl towards the black marker. I have to take my hand and turn it upside down so that my fingers will curl towards the black marker. Then my thumb is pointing downward, so if I do blue crossed with black, the cross product would point downward. Okay. That's our right hand rule. Okay. So, knowing that I can take the cross product, if I start with non-zero, non-parallel vectors, I'm going to get something that's mutually perpendicular to the two vectors I'm crossing. That narrows it down to one of two directions, and then the right-hand rule tells me which of those I get. Notice, though, that does tell me that the cross product is not going to be commutative, because if A crossed B pointed in that direction, but B crossed A pointed in that direction, they're not the same vector. Okay. All right, so let's just practice with this. Let's let V be 1, 2, 0. Let's let W be 2, negative 3, 1. Notice these two vectors are not 0, and they're not parallel to each other, because if they were parallel to each other, they would be multiples of each other, and they clearly aren't, because there's nothing I can multiply 0 by that's going to give me 1. All right, so here I have two non-zero, non-parallel vectors. If I wanted to find a vector mutually perpendicular, and I can use the word perpendicular rather than orthogonal in this case, because I know I'm not going to be getting the 0 vector. I'm going to be getting a non-zero vector, and the angle it makes with these two non-zero vectors will therefore will exist. Okay. So find a vector mutually perpendicular to V and W. The cross product gives us a very quick way of doing that. We simply calculate V cross W. So V cross W, that's going to be my symbolic determinant, I, J, K in the first row. V, the first factor, goes in the second row, so that's 1, 2, 0. W, the second factor, goes in the last row, so that's 2, negative 3, 1. And then I just work out that cross product. Okay. So for the i's, that's going to be my first component. I'm going to get this 2 by 2 determinant. That's 2 minus nothing. That's 2. Now for the j's, I'm going to get the opposite of this 2 by 2 determinant. And to make sure I get the opposite, I'm just going to calculate it backwards. So that would be nothing minus 1 gives me a negative 1. And then for the k's, I'm going to get this 2 by 2 determinant. Negative 3 minus 4 is negative 7. So here, that was very quick, we found a vector that's mutually perpendicular to V and W. And I can check very quickly that they are perpendicular, they're both non-zero, and they're orthogonal. Quick check. If I do the dot product, I get 2 minus 2 plus nothing is 0. If I do the dot product with W, I get 4 plus 3 minus 7 is 0. Excellent. So it worked out pretty nicely.